It goes by many names. You might call it the bell curve. You might even call it the Gaussian curve. You might call it Moivre's curve. I don't know how to say his name, so probably you don't do that. I think you know what I'm talking about. The normal distribution, especially because it says it right. Welcome to the 5-minute lecture series. This is Statistics. I am Abraham. I'm your host. Let's get started. Before we get into the normal distribution, let's once again define what a distribution is. The distribution of a statistical data set or a population is a listing or function showing all the possible values or intervals of the data and how often they occur. It's really important in this course to understand what a distribution is because it's pretty much everything we're going to talk about the entire course. This is an example of a normally distributed curve. It is basically the model of a histogram, where the vertical axis represents the frequency of the values, and the horizontal axis represents the values themselves. The normal curve is denoted with the notation n of mu sigma, or in this example, n of 30, 5. Here's some facts that I think you should know about normal distributions. They are symmetric, never skewed. The mean, median, and mode are all equal. The area under the curve represents 100% of the observations. You'll understand why this is super important a bit later. We can use a z-score transformation that will allow us to compare normal distributions that have different means and standard deviations. Hopefully this fact will become clearer in the near future as well. This fact is thrown around quite a bit, and I think it's mostly useful to help describe what the normal distribution is. So here it is, the 68, 95, 99.7 rule. It's basically describing what percentage of observations you'll find under the curve within certain standard deviations from the mean. i.e., you'll find 68% of the observations within one standard deviation of the mean, 95% of those observations within 2 standard deviations, and 99.7% within 3. Perhaps, knowing that most of the observations will fall within 3 standard deviations, if you were to find an observation that appeared 10 standard deviations away from the mean, you probably would realize that it's either really a rare find or it's just plain wrong. Now let's talk about z-score. And as I said before, z-score is just a way for us to compare different normal distributions. A z-score in essence standardizes values from the curve. It not only helps us compare distributions, it also allows us to answer some questions about the distribution we're looking at. The following scores are from IQ tests. It's denoted by n of 115. It represents the distribution of scores for every human that has ever taken the IQ test. Let's answer some questions. Let's start with an easy one. Suppose we want to know what percentage of people have scored less than 100 on the test. Since the distribution is symmetric about the score of 100, maybe you would guess that it'll be roughly 50% of the people. Let's apply the z-score formula and look at a standard normal table to find out the answer. First, the z-score. Z equals 100 minus the mean of 100 divided by 15. The result would be 0. Next, looking this up in the standard normal table, first start at the left side and move down to the row that your number is in. Our z-score is 0.00, so we stop at the first row. Then you would look at the columns. In our case, it's the first column. The value in that spot is 0.5000, which means that 50% of the data is to the left of a z-score of 0. Sweet, so our intuition matched the table and the formula. Let's try a harder one. Suppose we want to know what percentage of people scored more than 135. Let's apply the z-score formula and look at a standard normal table to find out the answer once again. Z equals 135 minus the mean of 100 divided by 15. The result would be 2.33. Now let's look at the table. So first find the number in the row, then the column. Note the number we have here of 0.9901. Now, if we naively use that number and applied the percentage, we would get 99.01%. But that truly doesn't make any sense. In fact, it's completely wrong. All right, let me explain. So, since we want to know the percentage of people that scored more than 135, we need to subtract the 0.9901 from 1. Then we get the stuff to the right of that point, which in this case is 0.0099. And making this into a percentage, we get 0.99%, almost 1%. Therefore, the final answer for this question is that approximately 0.99% of people score higher than 135 on the IQ test. And that's it. In this video, we covered some basic facts about normal distributions. We covered a couple of examples using the z-score formula, and we just generally had so much fun, right? There's a lot more to it, but for now, this is a good base. All right, so in the next video, we're going to start talking more about data collection. If you have any questions or comments, leave those in the comment section below. And as always, thanks for watching.